The Semantics of Boolean Logic by Aidan Delaney and Genevieve Smith-Nunge. Hello, and welcome to the fourth video in the series titled Propositional Logic. In this series of videos, we explore the reasons for developing the formal system of propositional logic, and we look at deduction using propositional logic. In the previous video, we presented the syntax of Boolean logic. The syntax is any sequence of symbols that can be regarded as a sentence in Boolean logic. In this video, we explore the meaning or semantics of Boolean logic. In order to discuss the semantics, we're going to have to agree to build the semantics of Boolean logic on top of other mathematical constructs whose meaning we're all willing to accept. In this case, we will explain the semantics of Boolean logic in terms of sets. We will also present the truth table for each of the Boolean operations. The syntax of Boolean logic states that the symbol top is a sentence, the symbol bottom is a sentence. If alpha is any letter from the characters capital A to capital Z, then alpha is a sentence. If alpha and beta are two sentences, then alpha wedge symbol followed by beta is a sentence. If alpha and beta are two sentences, then alpha V symbol followed by beta is a sentence. Finally, if alpha is a sentence, then the negation of alpha is a sentence. Our definition of the semantics of Boolean logic will follow this structure. The top symbol is our symbol for true. Often people use capital T to denote true. This looks quite similar to the top symbol. However, the symbol capital T is a letter between capital A and capital Z. Therefore, if we use the capital T as our symbol for true, we would have to ensure that we could not use the same letter to denote a proposition. It's a technical distinction, but precision in technical matters is necessary in logic. It's also worth noting that some people use the digit 1 to denote true. It really doesn't matter what the syntax is, but in our definition, we use the top symbol to mean true. To represent true, I will draw the following diagram. The diagram is an empty rectangle. The rectangle represents the universe, that is to say, everything. The bottom symbol is our symbol for false. Again, different people often use a capital F or the digit 0 to represent false. To represent false, I will draw the diagram for true and then shade in all the bits of the diagram that are false, that is to say the entire rectangle. The syntax states that any capital letter is a sentence. The meaning of a letter asserts that the proposition represented by the letter is true. If the chosen letter is, for example, capital X, then the semantic states that X is true, or X equals the top symbol. A more visual way to represent this is to draw the diagram for top and represent the proposition X by drawing a contour labelled X. Now we get on to the more interesting cases. The first is the meaning of the symbol wedge, which we pronounce AND. The usual presentation of the semantics of AND produces a truth table. So if the sentence states alpha and beta, then the truth table contains 4 rows. Each row provides the meaning of the AND operator, where alpha and beta evaluate to combinations of true and false. This does define the meaning of AND, but some further clarification is required. To make this explanation short, I'll introduce some technical language. The symbol wedge is an operator with 2 operands. The 2 operands are alpha and beta. The table states that there are 4 cases. One case where both operands evaluate to true, then the AND operation evaluates to true. In each of the other 3 cases, where one or more of the operands evaluates to false, then the AND operation evaluates to false. It is important here that we follow the very technical definition of the semantics of AND. We cannot apply any common sense or prior knowledge of the meaning of AND from natural language. I prefer a diagrammatic explanation of the meaning of AND. I'll go through an example of A and B. We draw the diagram we previously used to denote true. To this, we add the proposition A. We then add the proposition B. Note how the 2 circles overlap. The meaning of A and B is the part in the diagram where the proposition A is true and the proposition B is true. We shade the part of A outside B and the part of B outside A to reflect this. We've now looked at the semantics of the top symbol, the bottom symbol, and the wedge operator. So we'll consider the semantics of the V operator and thereafter the negation operator. When considering the meaning of the V operator, pronounced OR, it is particularly important that you do not apply your prior knowledge of the natural language meaning of OR. In natural language, we might say you can have the red or the green item, when we mean a choice between the two. The formal semantics of OR in Boolean logic differs from this intuition. To see how, I'll first present a truth table, then I will draw a diagram. The truth table has 4 cases. The meaning of OR states that if at least one of the operands evaluates to true, then the OR operation evaluates to true. The OR operation evaluates to false only in the case that both operands evaluate to false. I'll now present a diagram explaining the meaning of A or B. We draw the diagram we previously used to denote true. To this we add the proposition A. We then add the proposition B. Note again how the 2 circles overlap. The meaning of A or B is the part of the diagram where the proposition A is true or the proposition B is true. That is the area inside both contours A and B. Finally, we present the meaning of the negation operator. As the negation operator has only one operand, there are only 2 cases to consider. In the first case where the operand evaluates to true, then the negation operator evaluates to false. In the second case where the operand evaluates to false, the negation operator evaluates to true. As a diagram, if we wish to express not A, then we draw the diagram we previously used to denote true. To this we add the proposition A, then we shade the inside of A to denote that A is not true. To conclude, in this video we have considered the semantics of Boolean logic. We have looked at each of the elements of syntax and formally defined their meaning. To do so we had to agree on 2 things. The first is that sets exist. The second is that if something is not true, then it is false. If we disagreed with either statement, then we would have to build an entirely different system of logic. Such different systems do exist. In the next video, we will explore some applications of Boolean logic. We shall start with some high-level examples and proceed to develop a small model of a simple piece of code.